either side of the main plot screen. So we have what we call a navigation bar, and this allows you to create new graph types. We have a math menu that allows you to perform math on the data sets that you plot or create in our software. Command display window, that's basically shows the communication between the lap or computer or your analyzer. So that's helpful for troubleshooting sometimes if you're having connection issues. And then we have the readings windows at the top that shows the raw data taken from the analyzer, and then the analyzer control menu, which allows you to control the sweep and set voltage injection levels. And then here we've got the plot main screen. We have the data set list for each plot is usually on the right side. You can hide or make visible various data sets from here, or you can even select, double click on the data set and look at it'll give you a spreadsheet of the data if you want to look at the raw data. And then we have a plot graph settings window where you can set the axes of the graph, and then the data set property windows where you can set the properties of the data set, like you could scale the data set, or you can change the channel ratios, which if you have more than one channel is useful, and or you can even name the data set, and you can add a description too for it and make it either visible or uninvisible. And the software is Python based, so it's platform independent now. We can usually compile it depending on, most of our customers use Windows, of course. As it says up there, we can save multiple graphs and multiple plots in one file. Our software uses the WinUSB driver, so there's no need to load any drivers. Usually if you have a Windows 10 laptop and above, you can just plug it directly in and it'll load the driver and start communicating with the instrument. This is our 4-channel model, but we have channels with 3 or 2 channel models. And the frequency range starts at 10 microhertz, and then you have an option of selecting either 15, 20, or 40 megahertz as the upper frequency limit that you want to measure. Each channel.
I think you mean 5 megahertz, 20 and 40. You said 15.
Oh, excuse me. 5, 20, and 40. Guess I'm flashing back to old analyzers. So this particular one has 4 channels. They're all isolated, and they'll float up to about 600 volts. And the generator is also. And then each channel has a frequency range, or a voltage range from 10 millivolts up to 500 volts peak. And that's like in 10 dB steps, or so 10, 30, 100 millivolts. And then you go to 1 and 3 volts and so on and so forth. So it gives you about 11 ranges. The channels are also DC coupled. That's why we can measure down so low. We have like what's called a DC offset, active DC offset cancellation on the input, since we're mainly interested in measuring the AC component of the signal and not the DC component. So we use that to reduce the DC so we can set our AC at an optimum range and get better resolution. A couple of our analyzers have what, they call it absolute phase, but basically the generator becomes a zero phase reference. That would be our 350C analyzer, which has 3 channels and a reference channel. And then we have the 8800 series analyzers. Those are used for measuring digital feedback loops. So we have 2 analog channels. We call a digital channel, which is really a communication channel using I squared C and a generator, So it's similar. It also has a reference channel like the 350C. And it needs to know what the phase of the generator. It needs to have a reference, zero reference, in it to be able to measure digital feedback loops.
I don't think it's gonna come into play here with Qualcomm's application, but we
No.
also make a digital, a motion control FRA,
Right.
with mod demod capabilities. We internally call the 9X because it comes in 2 or 4 channel configuration. Go ahead, Michael. Didn't mean to
Yeah.
interrupt you there.
No, that's all right. But some people are interested in the digital domain, so I just thought I'd mention that. I don't know how familiar you are with using these type of instruments. Have you ever used them before, Derek?
No, not really. We have not.
Okay. Okay. Well, we are using a method developed by Dr. Middlebrook on how to measure a loop, open loop gain with the loop closed. So that's how we do it. So it makes it a lot easier. You don't have to bias up the loop. You can just connect our injection generator in series with the loop. So I thought I'd also go through, just run over the stability criteria and then how to do the measurements and then how to system, or I should say real world measurement systems. You really measure the phase margin and the gain margin from the 0 degrees or 360-degree phase line. The way I was taught in school is you measure phase margin from a 180-degree point if you're trying to determine stability, but that doesn't take into account the inverting 180 degrees phase shift, inversion of negative feedback. So usually when they're talking about that, they're talking about the final 180 degrees of phase shift and not the entire loop. But ours measures the entire loop. So this is basically what you would see if you measured a DC-DC converter. You're going to have very high gain at low frequencies. It's going to cross over in probably in the tens of kilohertz range or even higher now. And you can find the crossover with our slide bar. You can have it go to the 0 dB crossover, and that will give you the phase margin. Or conversely, you can go to the 0 phase crossover, and that will give you the gain margin. I don't know. Most people only bother with the phase margin, but some people do specify the gain margin as well when they're measuring these loops. Yeah, this is sort of what I was talking about, that the loop gain is actually negative because it's negative feedback. So you're going to have an extra 180 degrees of phase shift when you're measuring plots with our software. And this is basically a typical block diagram of a DC-DC power supply. typically we have, almost everybody selects an injection point between the resistor voltage divider and the output of the power supply. That's where you inject your signal. And once you've got that correct injection point, you can measure any part of the feedback loop, such as the power stage itself, the error amplifier, or the entire feedback loop. So, and this is just the criteria for selecting that point, that injection point, is that all the feedback needs to go through that, or has to be confined to a single path when you inject. You can't have any parallel paths or your results will be off. And the other is, since we're doing a voltage injection, we're injecting a voltage, so we want to be driving from a low impedance into a high impedance. And where we typically select the injection point on a power supply is perfect. Out the one side of the injection resistor is seeing a very low impedance from the output of the power supply, and then a very high impedance. The other side is seeing a very high impedance feeding into the resistor divider going to the error amplifier. So, and I've sort of talked about this earlier. Once you've got the correct injection point, and in this case, we have a 3-channel analyzer. So besides putting channel 1 and channel 2 on either side of the injection point to measure the loop, you could put another channel on the output of the error amplifier, and that allows you to measure do one sweep, and you can measure all the transfer functions in your feedback loop, like loop gain, modulator gain, and of course the error amplifier gain. But if you're designing, you're mainly interested in the modulator or the power stage, because that is what you're going to use the error amplifier to compensate. Okay. And this is a demo buck that I've used to demonstrate how to measure feedback loops. And here again, what I was talking about earlier, R7 at the top here, this is where you would inject between test point 8 and test point 7. You would also connect channel 1 for test point 7 to ground. And then you would connect channel 2, which would be the output of the loop, to the output of the power supply and ground. So keep channel 1's on the input, right? Which feeds, this comes over here. And then if you were going to measure the power stage, you would connect the channel here on the comp pin, which is the output of the air amp. This particular air amp is a transconductance air amp, so all the compensation is on the output of the amplifier. And then you would measure from the comp to test point 8, and that would give you the power stage, which is, if you're trying to design a air amp, is very important, that measurement to make. If you're just checking loop stability, then you only really need to, measure the total loop. It depends on what you're interested in doing. Are you doing testing or are you doing design, Derek?
A little of both. I
both.
want to see basically the response as we tune what you have,
Right.
the comp pin.
Right. So you're basically doing doing design.
Testing a already established design.
And you're going to test too, I know, but some people only do tests, and like test engineers. Just wondering. And for this particular power supply, I should go back. Okay, yeah, I'll show you my test setup for this. This has a switching frequency of 480 kilohertz, which is why I put the stop frequency on my sweep at 480 kilohertz up here. I start at 10. I'm going to stop at 480. There's no point going past 480. Don't have any sort of relevant control after that point. You have log sweep, which is steps per decade. As a matter of fact, I think I'll switch over to my laptop. Just so I've got the software open. Sure. Can you see my software screen?
Yes.
Yes, okay. So so this is the test setup I set here. It was start frequency, you know, as low as you can go. Stop frequency, that's going to be your switching frequency usually. You don't have to go that high, but a lot of people do. Steps per decade, that just gives you the number of steps per a number of points each decade of the sweep. You can also do a linear sweep where you go by steps and hertz. So, but typically most people use the log sweep since they're using log plots and the points are evenly spaced. And then right here we have the AC volts. I'm usually setting that to around 40, say 40, I'll put 40 millivolts in here. Since we're directly connecting to the power supply and we don't have a step down transformer, you really don't need to inject that much signal to get a decent plot. So I usually start between 20 and 40 millivolts and then increase it as necessary. We don't need any DC out because we're not biasing anything up. Rest of these are standards waveform sine. Output impedance is 50 ohms. We could go into the servo too. Might try that later. That allows you to set your output depending on what you want to drive your channel level to. So if you want to drive your channel level here, I'd say 2, that would be a higher channel, 30 millivolts. And that'll vary as you go through the sweep. It tends to cause the injection level to drop as you sweep along. You really don't need, you need a lot of injection level at low frequencies and high gains. And once you get down to a lower gain, you don't need so much injection level to get a good plot. Plus you can overdrive your plot. So and these measurements are small signal measurements. So you really don't want to inject large signals into the loop. It can cause it to distort and even throw your results off. So you need to start small when you're doing injections and then work your way up. And then down here, integration time, you could set it to either cycles of the waveform, which works really well at low frequency if you're measuring low frequencies, or you can measure by time. Here, I 3 seconds is usually pretty decent. You might get away with fewer seconds, so I wouldn't go below 1 second. The longer the integration time, which is sort of the inverse of what they call a bandwidth on a network analyzer. Usually the network analyzers use bandwidth frequency to set their how long they're going to accumulate data, whereas we use time. Since we're making very noisy measurements, we use long integration times because that gives you very narrow. If you know anything about discrete Fourier transforms, they're like Fourier transforms, but the longer the time, the narrower the band around that. It's like a notch filter around that frequency that rejects noise. So you get better results at longer times, but the cost is the measurement takes a lot longer to complete. Other analyzers they use very fast times, but then they use like sweep averaging to get rid of the noise, whereas we try to reject the noise from the very beginning. Down here, you can also set the input impedance of your channels. You can't set them independently. They're either all 50 ohms or they're all 1.6, or I should say 1.6, or 1 mega ohm, excuse me. So, and then at the bottom, we have what we call maximum change between data points, which is a useful feature if you're measuring resonant points where the gain and the phase have very large shifts. So you could set I typically use phase. You could set the phase setting so that it will take what I want to say, so it'll take a point every 20 degrees. So what it does is that you might set your plot to take 10 points per decade, but once you get around that resonant point, it'll start taking more points. So you'll get a better outline. You can miss a lot if you just have a fixed set of data points. And then once you get past that sharp phase and gain shift, you can it'll unwind itself, so go back to the original setting. It's just looking for a point where the phase shift isn't greater than 20 degrees, and so once it gets to a certain point, it'll unwind itself and it'll speed your sweep up considerably because of that. And at the very bottom, we have some different operating modes. The 350B operating mode is where there were some complaints about how we send out a pulse length, of like a second, and then once we're done with that frequency, we shut the output off, go to the next frequency, and then turn the output on again. And 350B operating mode is more of a continuous frequency change. So the output really never turns off. It just smoothly moves from, if you shut it off like that, that's an issue for like servo mechanical people. They don't like that very much. And we also have like a high noise algorithm. If you have a very noisy circuit, it'll help it'll help take quicker plots, I should say, because it'll try to keep you from getting trapped at one point where there's so much noise, it's stopping you from finishing your sweep, because our channels auto range, and if they're continually changing ranges, they will never settle down and take a measurement. So that's what that's useful for. We also have the ability to do DC and AC circuit tests. So we take into account the AC signal when we're doing measurements. That's typically, though, usually for an impedance measurement. And then we have the ability to, our default mode is auto ranging, but we have the ability to set ranges. Sometimes you'll just get a range change that throws your data off, and you can just fix one of the channel ranges or both, you know, to get the correct data if you know where your ranges need to be. So that's how we set it up, and this is how I would start. Let's see, I'm going to talk to the analyzer here. Okay, so the window at the bottom is showing the readings right here that I'm getting. I'm measuring the plant or power stage here. And I'll just have it run a sweep. So I'm measuring the power stage right at this point. I did some measurements earlier just to confirm everything was working okay. And this thing's been running for a while, so I'm not surprised the gain and phase didn't shift a little bit after it warmed up. I can also do a gain. I've only got a 2-channel analyzer, so I'd have to go over and change the connection so I can measure the total loop gain if you're interested in that. I'll switch back to the presentation. Oh, back on the presentation. Click on this plot. Okay. And this is a plot of that power supply that I showed you earlier. And I have a slide bar there that you could set automatically to the 0 dB cross, and it'll give you the phase margin. And this is the power stage, which I'm measuring right about now, of the same power supply. And here is where you can start your design. I selected this point of 30 kilohertz as my crossover frequency for my feedback loop. And there's an import button on our slide bar that you can use to, I'll show you that. I can use to import data into the feedback loop. And here's the methodology for doing loop design. So that's what we're doing right now, is measuring the control to output transfer function or the power stage or the modulator, whatever you want to call it. And I decide on a loop bandwidth, the crossover point, and what we want the phase margin to be at that crossover point. And the gain's pretty easy to calculate there. You just want your feedback loop to cause the crossover to be 0 dB at 30 kilohertz. And then we design an error amplifier for the boost using the measured phase at your desired crossover point and the phase margin. And by subtracting 90, that gives you the phase boost that we need to get from the error amplifier. So this is a really old slide, but it pretty much shows you what they're doing here is they're just trying to force the crossover by manipulating the gain or moving the gain up and down to cause the gain to cross over at the point that you want to. And then for the phase, they're moving the low frequency zeros and the high frequency poles, and they're moving them back and forth. The further apart they are, the higher the boost you get, and the closer they are together, the less phase boost you get. And we use that to manipulate the modulator and get the correct phase margin at crossover. So yeah, these are the numbers I imported from that previous plot into our circuit analysis and synthesis menu so we can design a feedback loop. I think I'll just go right back to the plot since it's done. It's done measure. Oops, did something wrong. There we go. Here's our software screen. Hopefully everybody can see that. I need to share it. Be able to see it now. What I can do here is I can grab the slide bar. I can tell it to go to the Unity crossing, but I really don't want it to. But that's what the phase. That's not where I want to go. I want to go to 30 kilohertz. So set that. And then I can import that into our analog synthesis menu. So at the top here, top left, we've got the crossover frequency and desired phase margin. And that's what you as a user would set, you know, what your desired goal is. And then to the right is the gain at the crossover frequency, and the phase, the crossover frequency that you imported from the plot. And I believe they use, go back, can't see it anyway. They use a transconductance amplifier, but I decided from the slope of the gain that frequency to use a type 2. I think they use type 3. So down here we have to set up the error amplifier. So on the left side, the type 3, you got type 1, type 2, and type 3. Now type 1 is just an integrator. And type 2 is, which I can show you. Type 1 is an integrator. So you just have a capacitor on the output of the error transconductance amplifier. And then the type 2, you have a resistor, capacitor, network on the output. And then type 3 is you have the same type of network on the output, but then you have another RC network, or sometimes only a C on the input to your design. But here I selected a type 2, is a transconductance. The input resistor is another user input everything is designed around this resistor, so you, the user, have to select it. And here I just use the one on the schematic for the power supply, which was 31.6 kiloohms. And then the input voltage, kind of deceptive, it's the output voltage of the power supply. So the input voltage of the air amplifier is the output, which in this case is 3.3 volts. You'll need the reference voltage. For this particular chip, it was 800 millivolts. And since the reference doesn't go through a common mode or go through a divider, the common mode voltage is also the same as the reference voltage. And then you need to enter the specs for your operational amplifier on the chip. This particular one has a 10 megahertz bandwidth, 69.8 dBs of open loop gain, and the transconductance is a 1.3 millisiemens, I guess, or modes. I think they're the same. And then once you get all this entered in, life gets easier for you. And you can compute the component values. And here I had the software round off all the component values. And you might see something like this big, that just means it's an open circuit. R5 really, this large number means R5 just doesn't exist, basically. So this gives you the values that you need for your air amplifier. All the values from here, over here, except when they're not necessary. So they'll either be 0 or very large. And you can use these values to build your air amplifier with. And here, after here, we'll make a circuit model. This is our little SPICE modeling program. It only does frequency domain type plots, but we use this to analyze the circuit. So we'll go to the analysis. Okay, it's set to 1 megahertz, no big deal. Typically, the output nodes are 1 and 2 on the circuit model. So the outputs here, the inputs here 1, outputs here's 2. That's a default setting. And yeah, you can select your minimum frequencies. Here, I can select 10 to 8, 40K. Still use the same number of steps per decade. And this will generate a plot for me. And then I can import this plot into the software. So there's my error amplifier right here. So this should be the plot you get when you add those compensation values on here on this page, component values. You can even print this little thing out. We'll print the schematic page for you. And once you get this, you can actually use the math menu. Let's see, this is plot 3, 4. Okay. I can go over to the math options menu here and okay, that's it. I'm going to multiply this by the synthesized. This is synthesized plot. I'll multiply this, and this will, and I can hit plot, and then this will give me my So. And this will give me the plot that is a combination of the power stage and my synthesized gain crossing, and it should be, yeah, it's close. It's very close to 60, which is what the target, my target value was there. So it's a little bit over. There's going to be a little variation if you round off the component values in here. It's going to throw everything off a little bit. There's usually not much you can do about that. So that gives you a good chance of reaching your target value. So you can use this to, if you need to tune the loop up. You may want to go further than this, but this is will give you a very good start on designing a feedback loop. Back to the presentation. Let's see. We got it all down. Yeah, I went through all this on the software. So that's it. I know you probably got questions, or there's one you want, something you want to know, or something I glossed over.
Yes.
Go
Could
ahead.
you go back to the error amplifier page where you were able to select type 1, type 2, or type 3 in the
Sure.
software?
Yeah, that one's pretty busy. Let me get back. I will go back to the we'll go back to the software here. Which screen? Now I'm back at the software. Okay, let's see. Here we go. Can you see
Okay.
that?
So I'm a little curious about how we get to this step. So let's say I already have a design, a board with these values in.
Oh, okay. Well, you could measure your feedback loop, or I mean your error amplifier, if you were just kind of curious. I mean, you can measure the power stage, or you can measure the error amplifier, you can measure the entire loop. So it's up to you. I mean, you could actually measure all three and then, see how they're going to work. If you just want to measure the entire gain, that would be the first step, I guess. If you've already got values in there, you can, check your gain and phase margin and see if they're correct or not. You don't have to go through this cycle. This cycle, what I was showing you was just what you would do if you wanted to. Why it's sticking to the bottom of the screen. What's that? Thanks. All right. Yeah. So what I went through was what you would do if you're designing. If you just want to look at it, you can just measure the Y. So you can actually just measure. Should just go back and show you show the presentation. Are you on 3? Sure. Can you see the presentation again?
Yeah, where you have questions.
Yeah, okay. Yeah, I was just gonna go back up this. Yeah, right here. So once you get the injection point, you can measure whatever you want. So if you want to measure the entire feedback loop, or you just want to measure either the power or modulator or the RM. So it's up to you. You can plug, you can measure all three if you want. If you're using a 2-channel unit, you're gonna have to do 3 different measurements. So if you have a 3 or 4-channel unit, you can do them all at once. So it depends on what you're interested in. If you're just interested in what your air amp looks like, or you want to know what the gain and phase margin, what do you want to know?
Okay, I see. And then let's say I don't, so let's say I do this injection method, I take the measurements, I look at the Bode plot, and I don't like where the crossover frequency is. So I could use your software and it would tell me what components I would need to set the crossover frequency and desired
Yeah.
phase margin.
Yeah, well, basically you would have to measure the power stage first. If you want to change the compensator or air amplifier, because that's how it works. You've got the power stage. There may not be much you can do to change the power stage. And then you use the air amplifier to get your gain and crossover, if you understand where I'm going to. So the first thing you need to do is measure modulator. And then once you've got that done, you can select the crossover frequency that you want in our software, and the phase margin that you desire. And then you can import the gain and phase of your power stage into our loop design software. So here, let me go back to our software. I think I got that open. Screen share. So, okay. So I have the loop design here open. So the 2 values on the left, the crossover frequency and the desired phase margin, those are the values that you want your power supply to achieve, basically, if you understand what I'm going there. You have to set those values yourself. You might not like the crossover frequency at 30, so you might want it at 50 instead. So I'm not sure the amp will handle this, but and then this control to output, this is from your power stage or modulator circuit. You import these values at the crossover. So this is 50, so I'd have to take this thing. I have to move this thing all the way over to 50. No, wrong one. I think it's this one. Yeah, this is what I did earlier. So I can I can import. Here's my import button. I can take that import. I could take that active slide bar that I set to 50 kilohertz and import the data values into. Why do you do that? Let's try this. Nope. I'm gonna need help because this. I don't know what the hell's going on. Okay, this is the 50 kilohertz. So this is my new crossover frequency I'm selecting here. These are the gain. These are gain and phase values that I'm going to import. when I hit that import to button, it shows up in the plot. It shows up in these windows. Or you can just read it off the slide bar and type in these values, but you need to know what the gain of the modulator, the phase of the modulator at 50 kilohertz, which is for at the new crossover frequency, 50 kilohertz that you want. And again, those are the only things I've changed. These are all the same from previously, and then I can get it to compute the values. Which of course it just doesn't. Yeah, I love how it just goes even further down the bottom of the screen where you can't see anything. It's not scaling right. Anyway, I'm probably, let's see, got an error. Sure. See, it says I don't have enough. I don't have enough boost. I need more. So I would have to go back here and try a type 3 amplifier. See if I can get enough boost up. I'm not changing anything else. I still want to cross over at 50 phase margin. The values haven't changed. And then I'll try this again. Compute. Okay. This one let me go. They let it pass. It said, okay, yeah. Not the greatest, but it works. So here are the component values, and they're automatically rounded off. You could set the rounding tolerances down here at the bottom. Here I've got 1% resistor and 10%. I mean, you don't have to automatically do it. Just set it yourself manually. And these would be your new model values. So that creates another spice net list for that circuit. And then I go to circuit analysis tab. I'm not going to change anything here. And then I'm going to plot my type 3 amplifier. Which is what I have to use. Type 2s just doesn't give you enough phase boost. It's, you know, you're only good to about 90 degrees with the type 2. If you got more than 90 degrees, then you have to use a type 3. So I can multiply these plots together. It's plot 3 and 6. So we'll go back over here and set. See what I'm doing. This is 3 synthesis, which is this plot here, which is synthesized error amplifier plot from the values that set in our design software, and then I multiply. And this is a new plot. So let me get a better display. So this thing's kind of getting a little busy. Let's see, get rid of this because it's too confusing. I want this guy, slide bar on it. I'll tell it to go to unity crossing. That should give me, you know, something close to what I want. It's actually crossing at 52, and there's about a 57 degree phase margin here. This generator plot, but that's pretty close to what I was looking for. Probably use a little bit more phase margin. But so that's how you can redesign a plot. I hope that answers some of your questions anyway.
Yeah, it does.
Yeah, so you can iterate, you can just go through several cycles if you need to. Some of it depends on, you know, your load to load and line. You have to check and see where your best, you know, the four corners, they call it high, you know, high line, low line, and then the high load and low load, and see which your worst plot is, because your loop gain will change with line and load. More on some power supply topologies than others, but so you know, you can, it's, this sort of integrates like design with your measurement is what it actually does. So, but you may only need to do